Hi, Tor, can you hear us?
Hi, yes,
Good morning.
good morning.
Whenever you want, we are ready.
Okay, thank you.
Okay, perfect. So we are going to start for the presentation. Hi everyone, we are the 5 students from the Mondragon University, and we are going to present a summary of our recent job, that it's the low-cost maximum power point tracking strategy and protection circuit applied to the Ayanz wind turbine with the screw blades. So first of all, we want to thank you for the invitation to expose our job, and congratulate you from the event. Okay. So this is going to be a summary. All the information on the technical data is available in our article that is published in Energies. If you scan the QR code, you can read the article, or if you have some interest or questions, you can write to us, and we are very happy to respond to you. So the index of the presentation will be the initial context of why we have done this project, the characterization and comparison of the wind turbine compared to other ones, the low-cost maximum power point tracking strategy, and the electronic protection circuit, and to finish the result discussion and some conclusions of the work. So the initial context of the project, we are going to first of all locate our university and us. We are located at the north part of Spain, between Spain and France, at the Mondragon town in the Basque Country. And here Spain is known from the solar and those kind of other renewable technologies, but we also have too much wind. And here in the north part, there are lots of wind parks. The last 2 years, for example, in Spain, around 2.5 gigawatts of residential self-consuming power plants were installed at residential and industrial areas. So a lot of small self-consuming installations have been installed in the recent years, but all those gigawatts are installed in solar technology. And we have one question: why isn't wind energy installed for residential use? First of all, the spares requirements are higher than the solar. The energy efficiency of the small wind turbines is smaller compared to the big ones. The initial cost and maintenance already. The permits and regulations, for example, have some blades, and in residential areas, we don't want blades or near from kids or colleagues. And the wind variability, these kind of wind turbines are situated or in the middle of buildings or towns, and the wind, they are not very laminar or good. So we have used the historical knowledge from Jerónimo de Ayanz and Beaumont to resolve or to propose a solution for contemporary issues. Jerónimo de Ayanz and Beaumont, it's an inventor from Navarra, Spain. Navarra is it's near from our university where it's located, and this inventor has invented some really useful things. For example, the steam engine, the air conditioning, and the first concept of the submarine. Also, Ayanz have patented in 1606 helical blades with an enclosure. So horizontal axis wind turbine with a tube that Ayanz is supposed to become more efficient and more safe to the people. So we took this concept from Ayanz from the 1606, and we have make a study to an actual commercial wind turbine.
Okay, thank you, Christian. So in this chapter, I will explain how has been carried out the characterization of this wind turbine, and also I will explain how the performance of the performance of the air turbine has been improved by incorporating an enclosure, as it had mentioned Christian. Okay, so the first step is to familiarize with the wind tunnel that has been used during this project. This wind tunnel is commanded in frequency. So we will control the wind speed by changing the frequency set point. To obtain the wind values that the air turbine is receiving, an average has been calculated from the winds recorded in 9 different points. In this way, very accurate results have been obtained. Once that we know the airflow that is generating the wind tunnel, it's time to know more about the air turbine that has been used in this project. As you can see, the chosen wind turbine is a commercial model Lion F1 AMW. It's a permanent Mayen synchronous machine, which is mainly oriented to urban utilization as it works pretty well with low wind speeds. Finally, you can see on the right bottom of the slide the electric power circuit that has been used. It is composed of a generator, a three-phase rectifier, a capacitance, and a variable resistance. Okay, so in this slide, we can see the performance of the air turbine at different wind speeds. In the first graphic, we can see the obtained maximum power, which is around 11 watts. To understand the second graphic, first we need to know what the CP coefficient is. By definition, the CP coefficient indicates the efficiency, which a wind turbine converts the kinetic energy of the wind into electrical energy. Now that we know the maximum CP obtained in this first experiment, the CP obtained in this first experiment is around 0.15, and is calculated with the formula that you have here. Okay, so once that we know the maximum power and CP values that we can obtain it from this commercial turbine, we have added a metallic enclosure to the turbine, mainly for two reasons. The first one is to follow the Ayanz patent, and the second one would be to find out if this enclosure improves the performance of the turbine. Moreover, with the addition of this tube, we are able to minimize the visual and acoustic impact of the turbine. Also, we can incorporate an anti-bird mesh to prevent any bird from getting into the turbine. Can you? Yes. Okay. So in this slide, we have the comparison between the performance of the wind turbine without the tube and with the tube. As you can see, the power and CP values obtained in the experiment with the tube are much better than the obtained ones in the experiment without the tube. At the maximum wind speed, the obtained power value is near 63% higher than in the test without the tube. As for the maximum CP value, it can be observed that they improve by 50%. Yes, here are okay. So therefore, it can be said that the tube is capable of capturing more air streams and direct them towards the turbine rotor. And in this way, we can increase the CP coefficient. One thing that we have tested is that if the wind turbine with the tube is not properly aligned with the wind direction, the generated power decreases significantly. For that reason, we have implemented a simple vane. You can click. This is the vane that we have added. And eventually, here is a demonstration video of the auto-orientation capability of the wind turbine. As you can see, the turbine orientates correctly and starts generating electricity.
Okay, so now I'm going to speak about the low-cost maximum power point tracking, or MPPT strategy we have implemented. So in case someone doesn't know what I'm talking about, the maximum power point tracking is a strategy that maximizes the power generation, so that in each wind velocity we can extract or reach the maximum power. So our group proposed a simplified power electronic conversion stage for small wind turbines, substituting the DC-DC converter and microprocessor that are typically used via three-phase impedance at the AC side. And we have some advantages, such as we reach quite a good MPPT approximation, as you will see in the next slides. It reduces the cost of the product. We use less element so that we achieve or we are close to the MPPT curve, and reduce the complexity of the system, for example. Please, can you pass the next slide? Yeah. So the idea is to take advantage of the variable voltage drop in the AC side of the impedances, as you can see in the below circuit. This voltage drop is in function of the current that grows the impedance. If the wind increase, the power generation increase. Increase the AC current amplitude, since the DC voltage is maintained constant in the right part, as you can see there. So first of all, we decide to test and make many tests so that we find the DC voltage optimus that was 40 volt. So we installed 3 batteries of 20 volt each in series. There you can see in the right graph in red the MPPT curve that is ideal, and we want to achieve it. In yellow only with a battery, and in blue, what is our main goal. And finally, you will see that we are near to that. So secondly, once we have determined the DC voltage, we implement the impedances. So to make it faster and to analyze more values, we use the MATLAB Simulink RE 2022A electrical engineering library software, and we implement capacitance and inductive series impedance. So to see what was happening and what could happen. In the left side, you can see the capacitance impedance graphic from 1 nanofarad to 200 microfarad, and you can see that they are not good results. They are not results. So we pass to the inductive series impedance, and in the right graph. And there you can see that there is a range of inductance that increase in all the wind speed. So for example, on analyzing the graphic, we take 0.32 Henry as a good result. And then in the next slide here, you can see the last circuit implemented with the 0.22 Henry inductive impedance and 40 volt in the DC side. And left side and right side, left side is simulated graphic and right side experimental graphic. You can see that the result that we are, the simulation result can be confirmed in the experimental test. So we achieve, or we get closer to the blue line in both cases, that is the MPPT ideal curve. And the red is the line with the impedance and the battery. So we get more power and we get close to the maximum power in each wind velocity.
Please. In this part of the presentation, I'm going to talk about the protection circuits. Specifically, I'm going to talk about the protection circuits attached to the batteries which are charged by the aerogenerator. This protection circuit has two main functions: one to protect from overcurrent the batteries, and the other one to supervise the voltage limits the battery has. It's important to mention that three different boards have been made, one for each battery that can be connected to the generator. These have been of 12 volts, 24 volts, and 36 volts respectively. Taking into account how the circuit works, we have a diagram here on the left side of the slide. First of all, batteries must be connected to the electronic circuit, and then the voltage they have is supervised. If the voltage is in the range AB, what does this range mean? Is the range where the optimus charge of the battery happens. It is called this way because as we have three different boards, if numerical values were put here, it wouldn't be so understandable. So if we are inside this positive or very efficient charge range, the generator is not braked and normal operation happens, which means that batteries are charged. If we go out of this range, the generator must be braked, so it's short-circuited by a relay and protection activates. Batteries are disconnected from the circuit. It's very important to short-circuit this generator. When we disconnect the batteries, the load disappears from the scheme. So the generator starts to spin faster and faster and faster with strong winds and can cause mechanical issues. To obtain the previously mentioned functionality, here we have in the top part of the slide the electronic circuit design. It can be seen as an addition of different sub-electronic circuits, such as in blue, the comparator window, in red, the Schmidt triggers, in yellow, the relay governance, in fourth, the relay in green, and finally, the fifth, in purple, the bus capacitance. If you have any doubts of the circuit, you can ask me when the presentation finishes, because we are not going to explain now how all the circuit works. Worth noting the importance of the efficiency of the board. It's not logic to create a board which consumes half of the power we generate. If we generate 30 watts and we consume 15 watts in the protection circuit, is not logic. So efficiency has been a very important point for us. So the power difference between the output and the input of the board is minimal. Important to mention too that the values that appear in the lower part of the table, in the lower part of the slide, are theoretical values, are not measured values in the board itself, and they do not take into account the rectifier losses. Another important point is the cost. Nowadays, when we are producing or we are going to be using this kind of boards in the industry or in some applications, the price is very important. And the industry standard for this kind of protections are microprocessors. So if we take into account the standard microprocessors and these boards, it doesn't depend, the 12, the 24, or the 36 volt board, they are much cheaper than all these microprocessors. And in comparison, they do the same work, being much more cheaper than them.
Okay, so now let's discuss the results and give some context about them. Please get to the next slide. Okay, so here we can see quite a standard way of comparing the wind turbines between them, which is usually using the CP and lambda coefficients. CP is basically, as Aitor mentioned before, the coefficient of the wind turbine achieving or capturing the wind turbine, the wind kinetic energy, and the lambda is basically how fast are the blades comparing to the wind speed. So as we can see here in the context, our wind turbine is quite well placed because the blade speed is quite slow, which is we will see later quite beneficial, but the CP coefficient is quite high. nearly as high as the Darius or its variants, or even a three-blade horizontal axis wind turbine. So please go to the next slide. Here we can see a bit more of a comparison between the different points, and especially the benefits from this wind turbine are the low rotating speed of the blades, which reduces the noise, reduces mechanical losses and stresses, which will also reduce temperatures in some parts of the generator. And also, as we mentioned before, it's quite an interesting achievement to introduce the prevention for the birth deaths. This will make a quite how to say this, a quite interesting point in which a bird will not go into the wind turbine, will not die. So it's pretty interesting for urban cities or urban places. You can go to the final slide. Okay, so let's conclude this. This wind turbine was patented for more than 40 centuries ago in 1606, as Christian mentioned before, and it still has pretty good features for the use in urban residential environments, as said before, because no bird will die, and even the screw blades cannot be seen, which is also pretty important for some people. And then the low-cost power conversion and protection electronics aim to facilitate the integration of small-scale wind power. This is quite important because usually the cost of the electronics is quite high, which makes harder for the small wind energy to be placed or to be useful. And well, all this analysis has been shown in open access, as we have said before. It's free for everyone. You can read more details about this study about the Ayanz wind turbine in our paper. You can scan the QR code if you want. And we are open now for your questions, if you have any.
Thank you very much. And I just noticed that I did a mistake while reading the program, so our break should have been a little longer. That's why you were probably surprised you were on a little earlier than expected. So I apologize for that.
That's why I thought it was a bit late, so, but no problem, no problem.
Yes, about the work.